I'm Jason Detwiler, and I went to undergraduate at Occidental College in Los Angeles, and I graduated from there in 1999 with a degree in physics. And then I went to Stanford University after that for graduate school for 5 years. I got my PhD in 2005 doing neutrino research. I was involved in measurements of what's called neutrino oscillation that proved that the neutrino has mass, and that was the subject of the 2015 Nobel Prize. Yeah, after that, I did a postdoctoral fellowship at the University of Washington and started working on the current trajectory of research that I'm working on, which is called neutrinoless double beta decay. It's essentially the search for the creation of matter without antimatter, which we know must exist because the universe exists and is made of matter, but nobody's ever seen it in the laboratory. So we're trying to be the first to do that. And then after 2 years in that position, I went to Berkeley Laboratory from 2007 to 2012 and worked as a Seaborg Fellow. And then I became a professor at the University of Washington. I've been here for 12 years since 2012.
That's really cool. And then how did you get interested in research in the first place?
When I was young, I was interested in math, and I thought I wanted to use math in some sort of technical field. And when I went to college, I was really interested in becoming an engineer. In order to get an engineering degree, you start with physics courses, and I started taking physics courses, and I just loved them. And so I decided to not do engineering and just focus on physics. And while I was an undergraduate, I got involved in research with a professor. And when I started doing research, I just loved it so much. And I was like, I want to do this as long as they let me continue to do this. And here I am. So, yeah, it was basically having those research opportunities as an undergraduate that really kind of fed my interest. And I just kept, trying to work hard and keep doing it.
That's nice. And then I know you kind of went over it a little bit, but in understandable terms to a high schooler, could you give me an overview of your research?
Yeah, so we're studying this fundamental particle called the neutrino. And the neutrino, like most people, haven't really heard of it. Actually, I didn't really know what it was, to be honest, until I was in graduate school. The neutrino is like the electron, but it has no electric charge. So it's kind of the same kind of particle. And they're actually very ubiquitous. The most common particle in the universe is the photon, the particle of light. And there's one neutrino roughly for every three photons. So they're actually very common, but we have almost no experience with them because they pass through matter mostly without interacting. And they're very hard to detect and to study. And we're still studying them today because they're so hard to detect and study. So it takes very advanced techniques and very large detectors to make progress with them. They've given us many surprises throughout their history, and the most recent one was at the turn of the century when I was doing my PhD. We discovered that they have mass. So they were thought for a long time to be massless particles. So, like the photon, the particle of light is a massless particle, and neutrinos were thought to be like that. Our entire theory of particle interactions, it's called the Standard Model. It was formulated under the assumption that these neutrinos are massless particles. So when we found that they had mass, it sort of broke this standard model of particle physics. And now we're trying to figure out how to give the neutrinos mass and add it to the theory. And it turns out that there's two options. And one option involves the idea that the neutrino might be the same particle as its antiparticle. The electron has an antiparticle called the positron. It's basically an electron with a positive charge instead of a negative charge. And the neutrino has something that we call the antineutrino, but it might be that those two particles are actually the same particle, and they're just spinning different directions, basically. And if that's the case, then the neutrino might help mediate these processes that can create matter without antimatter, which addresses this bigger question in physics, which is like why the universe exists. So it's kind of like a really exciting new direction that followed directly from my graduate studies. And to do these studies, we make these giant detectors in underground cavities because our detectors are so sensitive that cosmic rays from outer space will just light them up and we wouldn't be able to see them. So we have to put them deep underground where the earth above the detectors is shielding out these cosmic rays and letting us make these ultra sensitive experiments. So I get to go to these like exotic places around the world, like a mine in Japan or a nickel mine in Canada or a gold mine in South Dakota in the Black Hills. And then there's also this laboratory in a tunnel that goes through a mountain in Italy, and that's where I'm doing my main research right now. Yeah, and build these extravagant contraptions and get them to work and make some exciting physics measurements for them.
Yeah, that's super interesting. I've never even like heard of that before. And then what were some of your most significant findings or publications?
Yeah, so my thesis was on an experiment in Japan. Now there's this giant experiment called Super Kamiokande that won the 2015 Nobel Prize, along with an experiment in Canada for discovering this neutrino mass. And we were making a very similar measurement. And the idea is that like if you have multiple types of neutrinos with different masses, then when a neutrino is born, it's quantum mechanically born as a mixture of multiple neutrinos of different masses. And as it flies through space, they kind of start to go in and out of phase with each other. And you can see the neutrinos sort of transforming into different types of neutrinos as they fly through space. That's called neutrino oscillation. My thesis project was like we were looking at antineutrinos that were generated by nuclear reactors around Japan because Japan has a lot of at the time had was running a lot of nuclear power stations for most of their electric power. And a byproduct of that is these neutrinos, and they would just fly to our detector and run into our detector, and we would be able to measure this oscillation. My first big result was observing this oscillation pattern for the first time. It didn't win the Nobel Prize, but the plot that we made shows up in a lot of quantum mechanics textbooks now. So that's very exciting for us. And then when I was a postdoc, I got involved in this experiment, the one in Canada that did win the Nobel Prize. And we were continuing on those Nobel Prize winning measurements, and that was looking at neutrinos from the sun. And what had been observed for a long time was it was called the solar neutrino problem. You could calculate how many neutrinos should be coming out of the sun. And on Earth, we would measure only about 1/3 of them. And that's because we were always looking for this particular type of neutrino. And what we did with this experiment in Canada was we measured all types of neutrinos and showed that we got the right answer. And so that means that the neutrinos were born as one type and changed into another type somewhere between the sun and the Earth. And that's why this project won the Nobel Prize. It was like a 3-phase measurement, and I got involved in the third and final phase. And that made a really nice measurement of this solar neutrino flux measurement. And then in my current research, so it's really searching for something that we're not sure if it exists at all. You know, we haven't made the discovery yet, and we're hoping that we do discover it in the next round of experiments. But so far, what I've been involved in is a lot of groundbreaking work in achieving new sensitivity for searching for this type of interaction. We're mounting the world's most sensitive experiment now to try to make the discovery, hopefully, in the next decade or so. There's a lot of theoretical predictions that we might be able to see it in the next decade. I have one more thing that's like a major result. So on a sort of a side project, in the 70s, somebody proposed a new type of interaction that neutrinos can have with matter. It's called coherent elastic neutrino nuclear scattering. It had never been observed before, and along with with a big team of researchers, we discovered that in 2017 and have subsequently made that measurement with 2 more different types of detectors. And so that has been another sort of major result that I've been involved in.
Yeah, that's like super cool. And then, like, what are the biggest challenges that you faced in research and how did you overcome them?
The biggest challenge is finding funding because research is expensive and you have to convince the public that it's worth funding. Most of my current funding comes from the Department of Energy, Office of Science, and the Office of Nuclear Physics. We also get some funding from the Natural Science Foundation. Well, in both cases, you're competing with lots of other scientists for funding, so you have to make your case, and that's really challenging. One of the reasons they give us funding to do this, you know, kind of obscure research is our research is actually a really great training ground for nuclear scientists. And nuclear science is an incredibly important field, not just for doing fundamental research, but also for, you know, managing the nuclear power industry or performing stewardship of our nuclear arsenal. You know, it's important for our government to have a well-trained workforce in nuclear science. And so I think a lot of the motivation to fund our research in the public sector comes from that need to have those types of students. So we take that sort of responsibility of training the next generation as one of our main goals. Being able to do this research is sort of like a treat for doing that. We also hope it's, you know, enticing for students and gets them excited about nuclear science in general.
Yeah, okay. And then in contrast to the last question, what do you enjoy most about your research?
And what I enjoy the most is it's like working on a little puzzle every day. Like I always liked doing crossword puzzles or logic puzzles or even my math homework. I often enjoyed doing math homework. And this is like problems that nobody's ever solved before. And I get to work on little aspects of it every day. And yeah, just the idea of coming across something new and trying to be creative and come up with a solution. And sometimes I come up with something really good and everybody starts to use it. So yeah, that's really fun. I really like doing that.
Yeah, that's really nice. And then which person or mentor in your field has made the biggest impact on you?
Oh, that is a very hard question because I've had so many like really important mentors. Like all the way from high school, my math and physics teachers from high school were really encouraging to me. Like I remember in eighth grade, the teacher there let me do some extra algebra work because I had just moved from another state and I had already learned what the students had learned. And so he gave me a separate book and like helped me go through that. Like that was very important for me. My undergraduate advisor was extremely important because he gave me my first research opportunities. That really gave me a love for research. And as part of that, I worked at this national laboratory in Los Alamos. And the guy who was in charge of the research there, he was very important for me. And then, of course, my PhD advisor was extremely essential and like really set such a good example for me and taught me how to do so many things and put me on a good path. But then also, like, my colleagues on all these experiments I've worked on, my postdoc advisor, my colleagues at the research lab, and now my fellow professors, like senior professors above me, like they give me so much good advice all the time. Like, I really couldn't have gotten where I was without making those connections and taking advantage of the opportunities that they give me. I've had so many good research mentors.
And then were there any pivotal moments in your research career that made you change topics or want to pursue a certain topic?
My undergraduate research was like the first thing I could find. And I would highly recommend that. Like, if you're interested in research, just try anything. Like, pretty much all research is fun. And that was in condensed matter research. It was high magnetic field research. It was extremely exciting. But when I went to graduate school, I decided I wanted to try a different type of physics. At my graduate school at Stanford, we were able to kind of go around and kind of shop around for different types of research. I had planned to do three. So the first group was in observational cosmology, which is an incredibly exciting field right now. Then the second one was in particle physics and neutrino physics. And my third one was going to be in biophysics. But when I got to neutrino physics, I loved it so much I didn't even go on to biophysics. I just stayed in neutrino physics since then. So that was a big pivotal point. Since then, it's been about, so in neutrino physics, we have like a lot of these big projects. And so after getting into neutrino physics, it's been about sort of like choosing what project I want to be on. And it kind of in a similar pattern, like in graduate school, it was like whatever that advisor was working on, that was my option. So I just started with whatever was available to me and just worked really hard at it and had a lot of fun. But then when I became a postdoc, I kind of had a chance to choose for myself within this subfield, what sort of projects do I want to be working on? And I chose this trajectory that's looking for the creation of matter without antimatter. It's called neutrinoless double beta decay. And I've sort of stuck with that as my main research track since then. And the extra things I've done have been like this coherent elastic scattering measurement. That was kind of like a side project. Those are kind of most of the pivotal moments.
And then where do you see your research field expanding to? So, like, what are some interesting topics that can be further explored within the next 5 to 10 years?
So right now we're running this experiment in Italy. It's called Legend 200. And we just started running with that experiment like a year ago. So it took us about 5 years to get it up and running. And we're taking lots of data with that experiment, and we're going to be analyzing that data and generating results and searching for this process for like the next 5 years or so. And then at the same time, we're putting together a proposal for funding for a much larger experiment. It'll be about 5 times the size of that. So we call it Legend 1000. It will also be in this mine in Italy, or this underground laboratory in Italy. If we get the funding for it, we'll start building it. I mean, we're essentially starting now, but we hope to get some major funding starting next year, and we'll be putting that together. And there's several other groups, other projects around the world that are doing a similar type of measurement and building giant detectors. There are competitors, but they're also our colleagues. And so in this subfield, there's a lot going on in the next 5 to 10 years.
Yeah. And then how did you find your passion for research, and how would you suggest a high schooler try to find their own passion?
I'd say just kind of take it step by step. Like I had no idea that I would end up in experimental nuclear and particle physics when I was in high school. I knew that I liked math, but like I wasn't doing winning math competitions and I wasn't like really good at chess or anything. I wasn't particularly into science or physics. I knew that my cousins who were good at math were engineers, and so I just thought, oh, I'll just go to engineering school. And then as you're making your path, you make the right decision for that time, but allow yourself to get interested in something and like try to figure out what drives you and motivates you to work hard. Like it does take a lot of hard work to work in science and research, but whether it's science and research or some other field, like try to find something that motivates you to work hard. And that's how you know it's a good fit. If you don't mind doing the hard work, then it's probably a good fit. And maybe, I don't know if that's a useful suggestion, but that kind of has helped me.
Yeah, okay. And then what traits do you think define a great researcher, and what type of traits are you looking for in a potential lab member?
When I take on a new researcher, like the first things we want to see is just basic good work ethic, like, showing up, doing the work that you're assigned, making good progress. And then at sort of the next level, I want to see like some creativity or like a really good sign is when I talk with a researcher who's working for me and I give them some ideas on like next steps because we're always talking about, oh, here's where we've gotten to. Let's strategize for what's some of the next steps. And if I give some ideas for the next steps, what's really great is when they come back and they've tried some of those, but they've gone off in new directions. They've like followed their creativity or had some ideas on how to solve the problem and taken it in new directions that I didn't anticipate. That's a really exciting situation. The top people all do that. I think also just having a passion for what you're doing. And it's something that you don't have to be passive about. Like you don't have to look for something that you're passionate about. I think you can become passionate about what you're working on. Like a lot of the people that I really enjoy working with, they just get excited about whatever it is they're working on and do it really well. And I think that's something I look for when I'm looking for researchers.
Yeah, okay. What kind of skills do you think a high schooler could develop, even if they don't have access to a lab or any of the tools that you guys have?
Yeah, one skill that high schoolers can already start building that we use all the time is coding. Now, AI is having a big impact in coding right now, but the type of coding we do is lots of calculations and like doing some really special things that at least so far AI is not very well suited to code for us. So doing efficient computations of mathematical functions and doing these, simulating particle interactions. It's analyzing data. That's what we use code for. And so, just learning Python is already going to, give you a leg up when you get to college, that if you can already start making plots of data and things like that, that'll give you a head start. And I would say like anything that you're interested in, just read up on it or watch YouTube videos, like, invest some time in those things and learn about them because the earlier you start learning about them, the more vocabulary and experience you'll have with them. You'll be able to talk about them more and learn those things more deeply.
And then just for a final question, what's some advice that you would give to a high schooler who wants to go into research?
The top one is like invest your time in it and, try to enjoy it and develop a passion for it and let that help you work hard, take it step by step.
Okay, so that's all the questions that I have for today, and thank you so much for meeting with me.